You know, Sydney, I got this doggone problem. I don't know where we are. I mean, there's a longitude problem. With latitude and longitude, to know where you are, you have to...
Beth, may I ask why you're lying on the floor?
General Daly, I was just talking with Sydney about the longitude problem. Hey, you run this whole museum, correct?
Right.
So you're a pretty smart guy. Can you explain the longitude problem to me?
Well, before you can solve the longitude problem, you have to understand what latitude and longitude are. Lines of latitude, called parallels, measure distance north and south of the equator. Lines of longitude, called meridians, measure distance east and west of the prime meridian. So that's latitude and longitude. But before you can solve the longitude problem, you need a clock.
A clock?
Well, you know, Beth, this is going to take a while to explain, and I've got a museum to run, so I'll send a couple of curators down here to give you a hand.
Okay, well, can we get it done in about 30 minutes?
Of course, because this is STEM in 30.
Hi, I'm Beth Wilson.
And I'm Marty Kelsey.
We are coming to you live from the National Air and Space Museum in the Time and Navigation Gallery.
This gallery answers a very important question. If you want to know where you are, why do you need a good clock?
Also in this gallery, you can see the Winnie Mae. This is the airplane that Wiley Post used to fly solo around the world. We'd like to welcome our online audience. You can participate by sending us questions. We've got experts that can answer them, or we may use one on the live show.
We've got a great group of students with us today. This is the Maryland Homeschool Group. Thank you guys so much for joining us today. Now, Beth, before we get going, I've got to know something. Why the dog?
Well, in the early 1800s, the United States wanted to map the Pacific Ocean, which you could only do if you had a clock, right? Now, Charles Wilkes headed up this voyage, but he was not a very pleasant person. So by the time the 4-year journey was over, no one was talking to him except the dog.
So why is it that we need a good clock to know where we are?
That is a puzzle with a lot of pieces. But let's start with the longitude problem.
Navigating at sea is dangerous, tricky business. There aren't any landmarks or road maps for the open ocean. So how do you know where you are and where you are going? In order to know where you are on a map, you must know how far you are north to south and east to west. Lines of latitude indicate position north and south, and lines of longitude indicate how far east or west you are. By the 18th century, mariners had become good at using simple angle measuring tools to determine the altitude of the stars and sun against the horizon to figure out latitude, or how far north or south they were located. The more complex problem they had was trying to figure out longitude, or how far east or west they were located. To know the longitude, one must know the time in 2 places at once. That requires a good clock and measuring the local time by observing the sky. Here's how it works. The Earth turns 360 degrees in 24 hours, or 15 degrees each hour. Local noon is determined by noting when the sun reaches the highest point in the sky. Every 24 hours, the sun would be back in its highest point in the sky. Suppose a navigator had an accurate clock that kept track of time, synchronized to the daily movements of the sky as seen in a port city. The navigator could then carry this clock on the ship, which would continue to show the accurate time in the port city. The local time on board the ship was determined by measuring the position of the sun, moon, or stars. Longitude was determined by calculating the difference between local time and port time. If there was a 1-hour difference between noon on the clock and noon on the ship, the navigator would know the ship was 15 degrees east or west of the city where the clock was set. A 3-hour difference would mean the ship was 45 degrees east or west of that city. The challenge was knowing the time at the home port while sailing miles away, and to do that one must have an accurate clock.
And now I'm joined by Dr. Andrew Johnston, who is one of the scientists here at the National Air and Space Museum. Andrew, why was solving the longitude problem so important?
Well, even centuries ago, there were vessels, there were ships crossing the oceans back and forth, but they needed to know where they were going and they needed to get to certain ports at certain times. And for that, you needed to understand your latitude and your longitude, no matter where you were in the ocean. And as we just learned, there were tools for understanding latitude, but longitude was a harder problem to solve.
And you have some of the tools here. Do you want to tell us a little bit about what we're looking at here?
Absolutely. These are some of the tools that a navigator would use on board a ship. One tool you might use would be a compass. This is a magnetic compass, and it actually aligns itself with the Earth's magnetic field. And this is a tool that's been used for many centuries. And what it does is it points north, south, east, west, no matter where you are. And it enables you to keep a constant heading, so you point your ship in the right direction. Another tool that we've got right here is a sextant. This is a tool that allows you to measure angles in the sky. So I could use it like this, where I look through the sextant with my eye, and I move this part forward and backwards with my hand here. It's moving a mirror up there. And I can measure how high an object is in the sky in degrees, the sun or the moon or the stars. It's a very important part of understanding your position. But the other important ingredient that makes the whole system work is you need a clock.
Right, and at the time they had pendulum clocks.
That's right. Going back in time 300 years, there were clocks that would regulate their speed by using a swinging pendulum, as you see right here. The pendulum goes back and forth every second, and the clock moves forward in time.
Now, we've got some friends. We're going to show you all how, why a pendulum clock would not work very well on the sea. So,
right.
Bring my friends up here. Andrew, if you want to put that down for me.
Absolutely.
So we've got our ship, and we have our clock, and now our friends here are going to make some waves. So,
right, so let's move.
Okay, now why would this not work?
Well, you saw before our ship started moving back and forth that the pendulum was going back and forth very regularly. But if you look at it now that we're on this pretend ship, the pendulum isn't moving back and forth in a regular pattern. It's because the ship is pushing it back and forth. That means a pendulum clock was useless for determining longitude at sea.
Now, there were people working on a clock that did not have a pendulum, correct?
That's right. Then there were certain clocks that were good enough to be used at sea.
And we are going to actually take a look at some of those clocks. So let's take a look at the clocks that would work.
Hello, my name's Rory McAvoy, and I'm the Curator of Horology at the Royal Observatory, Greenwich. My job is to help people understand the history and the importance of our collection of around about 2,000 clocks, watches, and other time-related instruments. Let's take a look at some of John Harrison's extraordinary seagoing clocks. The ones that you see here were recently on display in the Folger Shakespeare Library in Washington, D.C. In the 1720s, John Harrison came up with a very special method of making clocks. His clocks did not require any lubrication, and they compensated for changes in temperature. He applied his methods to make a clock that could be taken on board a ship to sea and used to calculate your longitude, that is, how far east or west you are of any given place. In 1736, John Harrison took his first timekeeper H1 on a sea trial to Lisbon. The timekeeper didn't perform very well on the outward journey, but on the return journey it worked much better. This success caused the Board of Longitude to be gathered for the first time to discuss John Harrison's achievement. Harrison admitted to the board that his timekeeper was not perfect, and they granted him money to make a second timekeeper. This timekeeper was completed in 2 years, but during the testing of the timekeeper at home in London, John Harrison realized that it had a design flaw. He went to the Board of Longitude and told them this, and they granted him money to start work on a third timekeeper. John Harrison's solution to the problem was to use circular balances. H3 took a total of 19 years to build. During the making of H3, John Harrison turned his ideas to a different approach. He commissioned a watchmaker to make a pocket watch with some very subtle alterations to the movement. John Harrison was very surprised at the positive results gained from these small alterations. So H4 was sent on trial to Jamaica. It performed brilliantly during the trial, but there were certain aspects of the behavior of the watch that they decided a second trial was needed. H4 was later taken to the island of Barbados, and again the watch performed brilliantly. So H4 performed well within the requirements of the Queen Anne Longitude Act. So John Harrison proved that a marine timekeeper could be used to navigate safely by. And he paved the way for other watchmakers to improve upon his designs and create timekepers that were not only accurate, but also cheaper. And in doing so, greatly improved safety at sea.
So Andrew, should we take some questions?
Yes, let's do it.
We have a video question first.
My name is Ellis, and my question is, do we still use clocks like John Harrison built?
Alice, really good question. We still have some clocks that look somewhat similar to what John Harrison built, but most times people don't use clocks quite like that. These days we carry little timepieces like these right here that work in very different principles. They're not mechanical timepieces, they use little electrical powers. So there are clock collectors that still have those kind of clocks, but we don't use them on a daily basis.
Okay, and we have an online question. How was precise time determined in the 18th century?
So back in the 18th century, when some of these clocks were first designed, there were timepieces like the pendulum clocks that would work for determining time on the land surface at least. And out at sea, you would use one of those timepieces as designed by John Harrison or other people after that. And so that's how you would actually determine, those are the best ways of determining precise time back then, would be one of these really highly precise mechanical timepieces.
Okay, and we have an audience question.
Yes.
How did the sailors navigate when they only had the pendulum clock?
Really good question, because there were people navigating and in boats crossing the oceans a long time before there were really good mechanical timepieces. For thousands of years, people were crossing the Pacific Ocean and getting to islands. You would use other techniques where you would follow the movements of the sun and the moon. You could figure out how far north and south you were looking at particular stars. You would follow wind and wave patterns. If you could determine your latitude, you could sail straight east or west. It worked, it just took a lot longer, and it was sometimes not as reliable.
We have another video question, so let's take that.
My name is Hunter, and my question is, were there any other designs for a clock to work on a boat?
Yeah, Hunter, there sure were. In fact, some clocks that were proposed to solve the problem of longitude used steel springs to power them. Others used weight-driven mechanisms. There were a lot of people that tried to make pendulum clocks that would work on a ship. That it was a pendulum clock that they tried to isolate the vibrations of the movements between the clock and the rest of the ship, although those designs didn't quite work out. So yeah, there were many different designs that were proposed.
Okay, so we have discussed mechanical clocks.
Right.
But there are other ways to keep time, and to talk more about that, let's go to Roger and Marty.
All right, I'm joined by Roger Connor. Thank you so much for talking with us today. So Harrison's clocks were good for what they needed to be good for, but we've gotten more accurate since then, correct?
That's right. About 90 years ago, a really important change took place. And scientists had begun to realize that if you took a specially cut piece of quartz rock, and you subjected that to electricity, it would vibrate at a known rate. And it would vibrate at well over 1 million times per second. And this allowed you to measure things very precisely. And what they were measuring was the speed of radio transmissions. And radio transmissions, they move at the speed of light, 186,000 miles per second, really fast. And so one of the things that you could do is if you sent out a radio signal, it would hit things on the ground. If, say, you're in an airplane, it would bounce back and the airplane would receive that signal. And you could now time, with that quartz crystal, you could time that signal and see how long it took, and then display that on a scope, a radar scope. And so that allowed pilots and other air crew to see at night or in bad weather. They could see through the clouds and find things on the ground up to 50 miles away, sometimes even 100 miles. This was a huge advance, so very important for World War II in the 1940s.
Now, that wasn't the only system that quartz allowed us to have, correct?
No, there were a whole series of different radio navigation systems that really came to depend on the quartz technology. One of the most important ones was something called LORAN, and that was long-range navigation. And one of the problems with radar is it didn't work over open oceans because there was nothing for the radar signals to bounce off of. So if you were in an airplane or a ship in the open ocean and you couldn't see the clouds to use your sextant to take a celestial sight, and you couldn't use radar to reflect off of other things, what you would do is you would use a series of radio transmissions that would come from pairs of towers, and these would be hundreds of miles away, and they would broadcast a signal at a slightly different time. And your quartz clock, your quartz oscillator on the aircraft would pick up that time delay. And based upon the time delay, you could plot on a map a line of position. Now, if you use two different pairs of towers, you could plot where those lines intersected, and that would give you an exact fix.
Awesome. So the Harrison clocks were good, but we got better with quartz.
Absolutely. So by measuring time electrically using the quartz crystal, you were able to do a lot more, be a lot more versatile.
Awesome. Well, you ready for some questions?
Absolutely.
Let's start with a video question.
My name is Imani, and my question is, who invented the quartz clock?
Hi, Imani. The quartz clock, the first one came out in 1927. So there was William Marrison and J.W. Horton at Bell Telephone Laboratory were the ones that invented that.
Cool. All right, let's go to an online question. Could ordinary people use LORAN, or was it just for the military?
Well, it started as a military tool. Radar, same thing. So after World War II, both LORAN and radar became widely available. So they were kind of expensive. They were both very difficult to use. So it was usually only going to be like commercial companies, ships and airplanes that would use the equipment in addition to the military.
Okay. Now we've got audience questions.
Where does quartz come from?
So quartz originally came out of the ground, and in fact most of it came from Brazil. So it was actually very important to get that Brazilian quartz, particularly during the 1930s, 1940s during World War II. Starting in the later 1950s, they actually figured out how to make quartz crystal in the laboratory, so they could artificially make it and didn't have to dig it out of the ground anymore.
All right, well, now they've got a much more accurate clock than even the quartz clock, and we had a chance to go to the U.S. Naval Observatory, so it's time to go check that out. I'm joined by Jeff Chester. We are inside the U.S. Naval Observatory's master clock, and this is a really big, boring room, but there's some incredible science going on in here. Can you tell us a little bit about that?
Well, this is basically the place where time begins, and time begins with atoms. And atoms tick at certain specific frequencies, and we can use that ticking of the atoms to create what we call atomic clocks.
But it's a pretty accurate clock, right?
It is probably the most accurate clock in the world. Our system has the capability of measuring time down to the femtosecond level, which in plain English is 1/1000th of a trillionth of a second.
Wow. Now recently there was a leap second.
The leap second occurs because there are actually two time scales. One kept by atomic clocks, one kept by the actual rotation of the Earth. So what happens is every now and again, these two time scales will drift apart by about 1 second, and when that happens, we let them tick 1 extra second in a particular minute and let the Earth catch up. That coordinates the two time scales, and that's what gives us what is known as coordinated universal time, which is the time scale that is used to base all civil time in the Earth.
Now, why is that important to us?
So by having a very precise time scale, we can synchronize activities in different parts of the world, but for a lot of us today, whether we realize it or not, time is extremely important for simple things like using your GPS to find your way to grandma's house, or making a call on your cell phone, or using your ATM card at the bank. All of that has to be synchronized with extremely precise time, or the whole system just comes down like a house of cards.
And that all basically starts here.
It starts here.
Awesome. Well, thank you so much for showing us around the U.S. Master Clock.
You're welcome.
All right, so Andrew, we talked about atomic time, and we also talked about astronomical time. Can you kind of explain the difference there?
Sure. If we go back in previous centuries, the way people always timed their lives was the rotation of the Earth. You would follow the sun. When it was light out, you'd be active, and when it was dark, you'd be sleeping, or mostly. And up until recent times, that was still the timepiece that we used. We used the Earth as a clock. But then, especially as in the 1950s, when atomic clocks became more available, we realized that the rotation of the Earth was actually not completely stable. The length of a day varies, a second here, a second there, because the Earth's orbit wobbles just a little bit. And we measure that now with atomic clocks. So instead of following the rotation of the Earth, that's our basis of the time. Now everything is timed using atomic clocks, like the ones you saw there and the ones that we have here in the exhibition.
Now, this is an atomic clock, but it's got a different readout up above than it does here. Why is that?
So this box that we have right here has an atomic clock inside, and it reads out the red numbers on the front, read out the coordinated time. That's that time scale that Jeff was just mentioning at the Naval Observatory. That's the time that synchronizes the entire world. And then it's plugged into another box in the back that displays the blue numbers in the back of the case, and that displays the local time, which is a couple hours off, so that museum visitors can set their watch.
Nice. Are you ready for some questions?
I sure am.
All right, let's go to a video question first.
My name is Tucker, and my question is, how do you measure how fast the atoms move in an atomic clock?
Well, Tucker, really interesting question, but it's actually not the speed of the atoms that really matters. An atomic clock like this has atoms in there. That's why it's called an atomic clock. And this has the atoms of the element cesium, and those are exposed to a certain electromagnetic field. And those atoms absorb energy and then release it very quickly. They absorb it and release it. They actually do that more than 9 billion times every second. You can actually measure that rate, and that's the basis of the time. So it's not so much the speed of the atoms, it's their behavior, how they absorb and release energy.
All right, well, we've got an online question next. Do other countries measure precise time?
Lots of countries do. Here in the United States, we actually have 2 national laboratories that measure precise time. One that you just visited, the Naval Observatory, but then there's another one out in Boulder, Colorado, that also measures precise time. Other countries all over the world also have precise time services. And then there's an international service that's actually headquartered outside Paris, where they take everybody's time signals. It gets transmitted over fiber optic cables and satellite links, and that forms the international synchronization that all the systems follow.
All right, well, we've got an audience question now.
Sure.
Who invented the first clock?
The first clock ever? Well, devices that measure time go back so far, thousands of years ago, that we don't know the individual name of people that were building devices that would use candles that would burn down and measure time. There were pots of water that would let water out at a known rate that they could measure time. But some of the first devices that you would recognize as clocks that had a pendulum was invented by Galileo, actually, a guy that he sketched out a design for a pendulum clock. And this is many centuries ago. And then after that date, pendulum clocks were refined and started keeping good time.
All right. Well, let's head back over to Beth, and now she's going to talk to us a little bit about something we can do with all of the stuff we've learned today.
I am here with Dr. Paul Ceruzzi, who is one of our curators in space history. Now, Paul, we have talked about mechanical clocks and quartz clocks and atomic clocks and how important that is for navigating, but you have a map and a compass.
I do, and this is how people navigated prior to the time of GPS satellites. And maps are still very heavily used and relied upon. These are produced by the US government. And you combine the map with a magnetic compass, which points toward the magnetic North Pole. And by combining lining up the map to the compass pointing north, you can so-called orient the map, that you line it up, and you can follow directions by setting a compass direction here by rotating this. And you can follow along by waypoints, and you can navigate across open territory. This is a wilderness area in the Allegheny Mountains, not too far west of here. And you can find your way with some very simple tools. Now, obviously, you've got GPS, a constellation of satellites overhead, 12,000 miles up there, that give you very precise location. Sometimes the GPS doesn't work. It doesn't work so well in a very heavy forest cover, for example, or if you're in a canyon where you have cliffs that block the signal. And sometimes maybe your batteries run dead. And if you've ever had a cell phone with weak batteries, you know what I'm talking about. So it's nice to know you got a map with you.
So this is a specific GPS.
Yes, it is.
And it takes satellite readings, and it'll tell you your positioning, kind of like the map, but
Yes.
from space.
It reads signals from at least 4 of those 24 satellites, or actually there's more than 24 up there. It needs 4, and it takes the signals there and finds your location anywhere on the Earth to a very, very, maybe the size of this room or so. It's quite accurate, and it works in all kinds of weather. But sometimes it's nice to have a backup.
And I can get the GPS on my cell phone.
Modern cell phones have GPS chips installed, and they also have an additional feature. I mentioned that there are places where GPS doesn't work, such as in this room, because the walls block the signal. But cell phone signals come through from a different network, from towers that are nearby. And because the phone company needs to know where you are, if someone calls you, they need to know where to send the phone call. Because the phone company knows where you are, you can locate yourself with the phone as well.
And we have something that everybody who's watching can do. We have hidden a geocache outside of the museum. The coordinates are on your screen. You can go to geocaching.com and you can get the app there, and that'll give you the coordinates also. We invite you to use your cell phone, your computer, your GPS, even a map and compass. And the first 10 people who find our geocache, there's something special in there for you. So I hope that you all join us in geocaching.
Sure.
Paul, do you want to take a couple questions?
Sure, absolutely.
All right, let's start with a video question.
My name is Shakira, and my question is, what happens if a GPS on a boat breaks? Is there a backup system?
Shakara, that's a good question. A captain of a ship should probably, if he or she's any good at her job, would have several backups. Ships carry compasses. They carry radio receivers that can pick up beacons from land bases, for example, Loran. And there should be somebody on a big ship who still knows how to use a sextant, although that skill is slowly dying out. But if you've got a sextant and if you've got a good clock, you can always navigate that way.
You can practice working a sextant in this gallery as well.
Yes, you can. That's right.
Let's take an online question. Is radar like sonar?
Is radar like? Yes, it is. They both work on an echo. You send out a signal. In radar, you send out a radio signal, which travels very, very fast. Sonar, you send out an audio signal, which travels at the speed of sound, quite a bit slower. But sonar has the advantage of working underwater, which radar does not do very well. And of course, that's the way whales and other deep sea creatures navigate themselves, by sending out clicks and hearing the echoes. So the principle is the same, yes.
Well, that is all the time we have for today. We hope that you will join us again next month on September 23rd, where we will be talking about redirecting an asteroid. So, Paul, thank you very much.
You're welcome.
Okay.